Welcome to Future Epoch, where we learn more about our world. Every problem that advanced civilization has ever faced eventually comes back to energy. Energy to heat homes, to run industries, to power the computers and networks that now govern daily life. For most of human history, accessing enough of it has been the central constraint on human progress. We found coal, then oil, then nuclear fission, and we grew. But each of those sources brought costs and consequences that we are still reckoning with today. Now, as the pressure to decarbonize intensifies and global electricity demand continues its steep climb, engineers are returning to an idea first proposed more than 50 years ago. An idea so large and so strange that it was dismissed for decades as impractical fantasy. The idea is this: build solar power stations in space where the sun never sets, where there are no clouds, no seasons, and no night, and beam that energy back to Earth. This is not science fiction. It is an engineering challenge. And a growing number of serious institutions believe it may be one of the most consequential ones humanity has ever attempted. To understand why space solar power matters, you first need to understand the fundamental limitation of terrestrial solar energy. Solar panels on the ground are extraordinarily useful, but they face an unavoidable problem: Earth itself. Clouds block sunlight. Night renders panels useless for roughly half of every 24 hours. Seasonal variation means that winter panels at northern latitudes produce a fraction of what summer panels deliver. And the atmosphere absorbs and scatters a significant portion of the solar energy that reaches it before any panel ever sees it. In geostationary orbit, approximately 35,800 kilometers above the equator, none of those problems apply. A satellite at that altitude receives sunlight continuously, collecting solar radiation roughly 8 times more intense than what reaches Earth's surface after passing through the atmosphere. A solar power station in that position would generate electricity around the clock, every day of the year, regardless of weather or season below. The mechanism for getting that energy to the ground relies on wireless power transmission. The electrical energy collected by the satellite's panels is converted into microwave radiation and beamed in a focused, diffuse signal toward a large receiving antenna on the surface, known as a rectenna, which converts the microwaves back into electricity and feeds it into the grid. The underlying physics are well established. The question has always been whether the scale and cost required to build such a system can ever be made genuinely practical. The concept was first articulated in 1968 when aerospace engineer Peter Glaser published a paper in the journal Science, proposing that solar energy could be collected in orbit and transmitted to Earth via microwave. The timing was significant. The Apollo program had just demonstrated that humanity could reach space, and the oil crises of the early 1970s would soon give the idea political urgency it had never previously possessed. By 1979, NASA had conducted a comprehensive reference study examining space solar power in detail. The conclusion was unambiguous. The concept was technically sound, but the economics were prohibitive at the launch costs of the time. Delivering enough mass to orbit to build a useful power station would have required expenditure measured in the trillions of dollars. The idea was shelved, not disproved, and for the next 2 decades it remained largely dormant, revisited periodically in academic literature, but never funded at meaningful scale. Then the landscape began to shift. The emergence of commercial launch providers, most notably SpaceX with its reusable Falcon 9 rocket, began driving down the cost of reaching orbit in ways that had seemed implausible a generation earlier. What had once cost tens of thousands of dollars per kilogram to place in orbit began falling toward the low hundreds. Suddenly, the economic calculation that had closed the door in 1979 looked entirely different. By the early 2020s, the idea had moved from academic curiosity to active government program. The European Space Agency launched its Solaris initiative, a formal multi-year effort to assess space solar power as a realistic contributor to Europe's clean energy future. The United Kingdom government commissioned an independent feasibility study, completed in 2021 by the engineering consultancy Frazer-Nash, which concluded that a space solar power station was technically achievable and could potentially deliver electricity at costs competitive with offshore wind once the capital investment had been amortized. Japan's space agency, JAXA, had been pursuing wireless power transmission research for years and had conducted ground-based demonstrations of the core technology. Then, in 2023, the California Institute of Technology achieved something that moved the concept from ground demonstration to orbital proof. A prototype spacecraft built as part of Caltech's Space Solar Power project successfully transmitted power wirelessly between modules in orbit and beamed a measurable amount of energy toward Earth. It was a small-scale experiment, not a power plant. But it was the first time the full principle had been demonstrated in space. The central engineering problem is mass. A space solar power station capable of delivering meaningful output to a national grid would need to be immense, potentially several kilometers across, and constructed primarily from materials that still need to be launched from Earth. Even with dramatically reduced launch costs, the mass involved is staggering. Current estimates suggest a single station generating around 2 gigawatts of electrical power would weigh in the region of 10,000 tons or more, requiring many hundreds of heavy-lift launches to assemble in orbit. This dependency creates a second problem. The technology for assembling structures of that size in space does not yet exist at the required scale. Both autonomous in-orbit robotics and ultralight photovoltaic materials capable of generating substantial power without adding prohibitive weight are active research areas, but neither is ready for deployment at the scope a functional station would demand. There is also the question of conversion efficiency. Energy is lost at every stage of the chain, from sunlight to grid electricity. Solar panels convert sunlight into electrical current with some loss. That current is then converted into microwave radiation for transmission, again losing energy in the process. The microwave beam travels through the atmosphere, where some fraction is absorbed or scattered. The rectenna on the ground converts microwaves back to electricity, again imperfectly. End-to-end efficiency estimates across the full system remain a subject of active engineering research, and improving them requires simultaneous advances across several independent fields. Public concern about the microwave beam is a further dimension that rarely appears in technical reports but cannot be ignored. Advocates are quick to point out that the beam would be intentionally diffuse, spread across a receiving area of several square kilometers, making its intensity at the surface far lower than direct sunlight. Studies commissioned by ESA and the UK government have found no credible safety concerns at the power densities being proposed. But the perception of a directed beam of radiation from orbit is a political and communications challenge, particularly for communities situated near proposed rectenna sites. If the engineering and economic obstacles can be overcome, the consequences would be substantial. Space solar power would provide something that no other renewable energy technology currently offers at grid scale: firm, dispatchable, baseload power that is entirely independent of weather, geography, and time of day. Unlike wind or ground-based solar, it would require no large-scale battery storage to manage intermittency, because there is no intermittency to manage. A sufficient network of orbital stations could supply continuous power to any point on Earth's surface, regardless of local conditions. The UK feasibility study estimated that a mature operational station could deliver electricity at a levelized cost broadly comparable to offshore wind, once the capital infrastructure was amortized across its operational lifetime. ESA's Solaris program has suggested that space solar power could make a meaningful contribution to European energy supply by the 2050s, though the agency has been careful to frame this as a potential rather than a commitment. The geopolitical dimensions are rarely discussed in technical literature but deserve attention. Whoever builds and operates space solar power infrastructure at scale would control an energy resource with reach across the entire planet. The geostationary orbital positions that allow continuous coverage of any given region on the ground are finite. Access to space, the industrial capability to manufacture and assemble large structures in orbit, and the financial and political will to invest at the required scale are not evenly distributed among nations. As the clean energy transition and the commercial space race converge, space solar power sits squarely at their intersection. The countries that move earliest and most decisively may shape the geopolitics of energy for the century that follows. The most important thing to understand about space solar power is that the limiting factor has never been the physics. The physics worked when Peter Glaser proposed it in 1968. It still works now. The Caltech prototype demonstrated that in orbit in 2023. What has always limited the concept is the cost and engineering difficulty of operating at the scale that would make it useful. What has changed in recent decades is that the trajectory of launch costs, materials science, and in-orbit manufacturing capability has shifted enough that serious institutions are willing to spend real money investigating it again, and credentialed engineers are willing to put their names on feasibility reports that say it is achievable. That does not mean it will succeed. The history of engineering is well populated with concepts that were theoretically sound and practically impossible. But it does mean that the accurate description of space solar power has changed. It is no longer a fantasy. It is an unsolved engineering and economic problem, and those are different things entirely. The history of energy is a history of transitions that seemed impossible until they happened. Coal-powered industrialization, electrification, nuclear power, and now the rapid expansion of ground-based renewables all passed through eras when the scale of what was being proposed appeared absurd to the people who would eventually see it become ordinary. Space solar power may follow the same arc, or it may remain at the edge of feasibility, perpetually promising and perpetually deferred. What the current moment has produced is something that has not existed for most of the past 50 years, genuine, institutionally funded momentum. Governments are commissioning studies. Space agencies are running active programs. University laboratories are flying prototypes. The launch industry is in the middle of a transformation that is rewriting the cost of access to orbit. The question that remains is not whether solar energy can be collected in space and returned to Earth. We know it can. The question is whether humanity can build the industrial and financial architecture to do it at a scale that actually changes the trajectory of the energy transition, and whether it can do so before the window of need is closed by other solutions. That is not a question the physics can answer. It is a question about will, investment, and time. And for the first time in a very long time, it is being asked in earnest. Thank you for watching. If you've enjoyed this content and want to see more, please consider liking the video and subscribing to the channel.